Hello, Mr. Chishtai, Tumpai, Titsinara, Chamroin, and the others. Guys, good to see you again. I hope you are all doing well. So let's just start the class, okay? So during the class, anytime, if you have any questions related to this course, Calculus 3, anytime you are most welcome, okay? You can ask. So guys, today we are going to have again 2 sessions. And the first session actually will be 30 minutes. And also the second session will be 30 minutes. And we are going to have break 30 minutes, okay? So we have class from 3 to 3:30. And after that, 4 to 4:30 or 4:35. 30 minutes will be break time. Chishta, is everything okay? Do you hear me well?
Yes, sir.
Okay, if you don't hear me well, let me know, okay? Because now I'm using Wi-Fi. If anything is wrong, I'll just change this to 4G and maybe 4G will be much better. Sometimes Wi-Fi is not so stable. So let's continue then, guys. As you know, we were talking about, what is it? Partial derivatives. Okay, first we started with functions of several variables. In our last class, we talked about the definition of functions of multivariables, especially functions of 2 variables, functions of 3 variables, and how to determine their domains and the range and their graphs, right? And also level curves and blah, 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 blah. And also some, what is it, open sets or open region or closed set or closed region, right? And how do we define an interior point or boundary points? And a closed set and the open sets. Anyway, these are the basic concepts in studying multivariable functions. And now today we are going to talk about limits and continuity in higher dimensions, okay? And also you will see that actually in a lot of, what is it, aspects actually are very similar to limits of a function of one variable. Yet actually there are some differences, of course, because now here we have to consider that a point, because for example, let's say if you're talking about a function of 2 variables, right? If you're talking about a single point in the region, we have a lot of different in a lot of different directions we can approach this point. But when we talk about a function of single variable, that means that we have to consider its function, the function over an interval, right? That means it's just a line segment, maybe including the boundary point or not. So that means that we have only 2 directions that we can approach the point, that is from right hand side or left hand side. And that's why we have the also, or that we studied about one-sided limits. And for a function to have a limit, right, left hand sided limit and the right hand limits, they must be equal to each other. Anyway, these are things that as we make a progress, you will have more intuition about these concepts. And of course, one more time, let me tell you, the only way to learn math is you have to solve problems. As you solve more different problems, you will gain deeper intuition. So let's start with, what is it, some informal definition of this limits. After that, we will see some examples, and I hope actually you will see what is it, the picture more clearer, let's say, after what is it, considering a few examples. So this section treats limits and continuity for multivariable functions. These ideas are analogous to limits and continuity for single variable functions, but including more independent variables. That means that the function may be a function of 2 or 3 or 4 variables, but of course, particularly in this course, as I told you, we will most of the time we will deal with a function of 2 or 3 variables. Sometimes maybe a function of 4 variables. So what we have here, limits for functions of 2 variables, continuity, functions of more than 2 variables, extreme values of continuous functions on closed and bounded sets. Okay, yeah, these are the formal definitions we have to go through, okay? And also by reading, by practicing, somehow also you will improve your mathematical language. Now, if you just remove, for example, the second variable here, y, it will be the exact copy of the definition of a limit of, what is it, a function of single variable. Okay, so we say that a function f of x and y approach the limit L, that is a limiting value of this function. right? You can just immediately, you can just imagine a kind of region, okay? And the function is assuming or taking all its input values from this region. And if you substitute some value for x and y, the function produces a real number, right? So here, the approach the limit L as xy, approach x sub 0, y sub 0. So that is a fixed point, and we just write it as here limits. Let me use here. Okay, here limits that's xy is approaching x sub 0, y sub 0. F of x and y equals L. Okay, if now we have actually imposing a condition. Okay, when we can write this expression, right? If for every positive epsilon, this means that for every positive epsilon, and usually this epsilon is small. And one student asked Mr. Kazam, how the epsilon is greater than 1 or greater than 5? Of course, actually, it works for everything, but usually the idea here is as we get closer and closer to this point, right? What is our point? Our point here is x sub 0. We are talking about kind of region. Let's say that is the domain of the function f. So domain of the function f, and here use different color here, and we are talking about this point. Let me just label this p sub 0. P sub 0 is a point whose x and y coordinates are x sub 0 and y sub 0. Okay, so the problem is that if I get closer and closer to this point, maybe in this direction or maybe in this direction, because the region I can actually approach in many different directions, right? And whatever the direction is, as we get closer, for example, let's say I get this much closer or this much closer, right? As I get closer and closer, does the value of the function, this f, right, xy, also get closer and closer to a certain value? Let's say this L. If it is so, then actually it makes sense to talk about the limit of the function. Otherwise, in one direction, if I get close to this point p sub 0, the function gets close to, let's say, number 5. If you choose another direction, you get close to this point, and function gets close to another point. At the time, that means that the function does not have limit at this point. Okay, so let's continue. So if for every positive epsilon 0, there exists a corresponding number delta, positive delta, such that for all xy in the domain of f, right? If you just pick any xy, that's actually here where this f of xy minus L is less than epsilon, whenever this 0 less than square root of x minus x sub 0 squared plus y minus y sub 0 squared is less than delta. Okay, what does that mean? It means that simply, again, if you're talking about a point, that's our x sub 0, y sub 0. Okay, here we have p sub 0. Okay, if you just show me any epsilon, all right, any epsilon, it doesn't matter, because when you just say any epsilon, here, if you're talking about the values of the function, let's say this value is L. This value is, let's say, this L. And let's say that one is epsilon neighborhood of this L. Okay, this one is L plus epsilon, and this one is L minus epsilon. Okay, so for example, for every epsilon, okay, that means that actually what is your precision actually? Like for example, how much should I get close to L so that we can just use as L as what is it? The value of the function at this point, at x sub 0, y sub 0. Okay, it depends on your precision. Maybe it is your 0.1 or 0.01. It doesn't matter. If you just show me any positive epsilon, right? For example, your position is this. Okay, can I just show you some disk centered at x sub 0? Okay, because here x minus x sub 0 squared plus y minus y sub squared is less than delta squared. It is the equation of a disk, right? Disk means if you just circle, we just consider the boundary point. We just say disk including all the points inside the circle. right? So we are talking about this disk centered at x sub 0, right? So that if you just pick any point from this disk, maybe this point, or maybe this point, or maybe this point, okay? And if you evaluate the value of the function at this point from any point here, it must give us a number between L minus epsilon and L plus epsilon. This is what we mean by this inequality, right? And that is actually the meaning of limits. So if for every positive epsilon, there exists a corresponding number delta, positive delta. Okay. What's wrong? Okay. David, can you hear me? David N.
Yes, sir.
Yeah, guys, sorry. I was expecting this problem. I don't know. When I use Wi-Fi, it suddenly disconnects, and now I had to change the 4G, and it takes time. So let's see. So that's why I'm hoping that, I don't know how you like it, but I prefer to teach in the class. I hope after 2 weeks we will meet at university campus and continue our classes there. Right, David, Tisinara, Chamroin, Chichtai. I want to see your physical faces, not only the picture on the computer screen. And also I want to hear your voices. Guys, anyway, let's continue. So actually the main idea is this, okay? We have already studied in calculus 1. Here we are just adding more parameters or more variables. So when you just add, for example, if you're considering a function of 2 variables, its domain is a region, or what is it? It's a plane, right? Because it is two-dimensional region. So if you're talking about a point, we can have a lot of different directions to approach this point. So it means that here, this equation, it may look a little bit complicated when you just have a look for the first time, but actually it's just the equation of a disk. Because if it is equal to delta, it gives us the equation of a circle whose radiuses are. But it is less than delta, means that we are talking about a region, right? Region that actually, what is it, consists of all the points inside this circle, but we don't have equal sign. That's why it's not including that boundary points. So that's the definition of this limits. Okay, so let's continue. So in the limit definition, delta is the radius of a disk centered at x sub 0, y sub 0. For all points x, y within the disk, the function values, this f of x, y, lie inside the corresponding interval, that is L minus epsilon, L plus epsilon. Okay, see here, this one is, let's say, the domain of the function. Okay, our f function, actually it takes all its input values from this region. So we are talking about this point, right? X sub 0, y sub 0. So if I just get closer and closer to this, right? If you just pick any point that is lying inside within a radius of epsilon, right? And what will be the value of the function? Is it between this L minus epsilon and L plus epsilon? And if it is so, that means that for every value of epsilon, that means, actually, what does it mean? It means that as we get closer and closer to this point, x sub 0, y sub 0 in any direction, right? And also actually the value of the function gets closer and closer to L. This is how we describe this limit. All right. How about the properties and the limit properties, or properties of limits of functions of two variables? They are all very, very similar, almost exact copy of them, but the only difference is now the function is not a function of single variable, but a function of two variables. So the following rules hold if L, M, and K are real numbers and the limit of f of xy as xy equals x sub 0, y sub 0 equals L. This limit exists. And the second one is limit of g is equal to M. So if these two limits exist, then some rule limit of f plus g is equal to L plus M. Difference rule, limit of f minus g equals L minus M. Constant multiple, if you just multiply a function by k, it does not change the behavior of the function. That's just equal to k times L. K is any real number. And how about the product rule? Product rule is f times g is equal to L times M. And the quotient rule, f over g, that is L over M. Of course, here M should be different from 0. Power rule, f to the power of n is just equal to L to the power of M. And root rule, nth root of f equals L to the power of 1 over M, or nth root of L. It's actually exactly the same properties, but here just differences. We are dealing with a function of multivariables. Okay. Compute the following limits. Let's see two examples about the calculation. Usually most limits, they are just straightforward, okay? Because, and sometimes it may need some algebraic manipulation if, actually, when you just directly substitute the values of this limiting, what is it? The point, right? This, for example, in the first example, 0, 0, if we have 0 in the denominator, at the time we try to remove 0 from the denominator. Otherwise, most of the cases, it is just straightforward. So, for example, compute the following limits. Now, let's say here, if, for example, when x equals 0, y equals 0, right? Or when x approaches 0 and y approaches 0 at the same time, x squared plus y squared, also it approaches 0. But in the denominator, we have 1. So 1 minus 1 is equal to 0. So what are we going to do with this? We try to remove 0 from the, what is it, denominator. How? By using just simple algebraic manipulation. We just multiply numerator and denominator by the conjugate of this expression, right? So equals, here we have equals limits as x and y approach 0 and 0. Here, if you multiply numerator and denominator by the conjugate of the expression in the denominator, what we have in the numerator, here we have x squared plus y squared, and times, here we have, let me just write like this, square root of x squared plus y squared plus 1. And here we have plus 1. And in the denominator, here we have a minus 1 times a plus 1, right? So when you just simplify this, the square of this expression, here we have x squared plus y squared plus 1. Minus, here we have 1 squared, that is 1. So now 1 minus 1 is equal to 0. And also this x squared and y squared, they cancel each other. So now we have this expression, limit as x, y approach 0, 0. Actually, we don't have fraction line. We don't have to write fraction line anymore. So here we have square root of x squared plus y squared plus 1. And the plus 1. So now if we evaluate this, we have no problem here. It's just 1 because here we are just using the property, right? We know that under the square root, right, this expression, x squared plus y squared, they are just polynomial functions. And usually polynomial functions, the limit of any polynomial function is equal to the value of the polynomial function at that point. So that's equal to, what is it? Here we have 0 plus 0 plus 1 and plus 1, which is equal to, what is it? 2. So the limit of this function f of x and y as xy equals 0, 0 will approach 2. How about in the second example, question B, to evaluate this limit as xy equals 0, 1, and our function is a function of two variables, x minus xy plus 3 over x squared times y plus 5 times xy minus y cubed. So now again, for example, if we just evaluate, is see here in the numerator, we have a polynomial function of two variables. In the denominator, we have also a polynomial function of two variables. And when is x equals 0, y equals 1, right? Here we have 0 and also 0, and this one is 1. Why? Because when x equals 0, it is 0, 0, we have 1. So we have no problem. So directly we can just evaluate this. So this limit is equal to, here we have 0 minus 0 times 1, it is 0 plus 3. In the denominator, 0 times 1, it is 0. 5 times 0 times 1, it is 0. Minus 1 cubed, it is 1. So which is equal to negative 3. Okay. How about another example? Also under the square root, right? Actually, this one is our polynomial function. Let me just write here this p x y. That is x squared plus y squared. When we say that it's polynomial function, because all the, what is it? The powers of the variables, they are positive integers or just zero, non-negative, let's say, integers. So here, directly we can evaluate this. So this limit is equal to, what is it? Limit, that is x, y, as approach 3 and minus 4. Actually, it's so weird. I need to write a bit smaller. Here we have x and y, approach 3 and minus 4 of this x squared plus y squared, right? So that's just equal to square root of 3 squared, it is 9, negative 4 squared, it is 16, which is equal to 5. That means that actually, if you are given this function, f of xy equals square root of x squared plus y squared, as xy approach the point 3 minus 4, the value of the function approach, what is it? Number 5. And how about in question D? In question D, actually, if it's a substitute 0 and 0 for x and y, we will have 0 in the denominator. Again, by multiplying numerator and denominator by the conjugate of this expression, y squared of x minus square root of y. So we can actually change this into another form. Here we have limit as x, y approach 0 and 0. So if you multiply numerator by square root of x plus y, here we have x squared minus xy, or even I can do like this. We don't have to do that. In the numerator, x is a common factor. Here we have x, here we have x minus y. Over, here we have square root of x and minus square root of y, right? And we know that actually this x minus y, we can factorize it as, because x is square root of x squared plus x minus, how about y? It is square root of y squared. So here we have a squared minus b squared. It's very basic identity in math. So that's equal to square root of x plus square root of y times square root of x minus square root of y. If I substitute here, as you see here, the square root of x minus square root of y, it will be gone. So let me just continue here. Now our limit will be, what is it? So that is limit as x and y approach 0 and 0. Here we have x times square root of x plus square root of y, which is equal to, now immediately we can evaluate. We have no problem with evaluating this limit. So it is x, right? It is 0, 0 times 0. So this limit is equal to 0. Chamroin, is everything okay?
Yes, sir.
Chamroin, how are you joining this class? With your laptop or telephone, iPads, tablets?
With a laptop.
Laptop. Good. Usually for online classes, of course, actually, not everybody can afford this. If you have laptop, you should join this, but of course you should just keep it away from your eyes, maybe at least ½ meter or 70 centimeters. And also at the same time, you can join with maybe iPad or tablet, right? And also to write a note. Maybe you want to share something, or just watching is okay. But sometimes if you want to also share something, immediately using annotation, you can write on the screen and share your ideas with your friends here. And of course, technology, spending too much time in front of technology is not good for our health. Let's see. Well, let's continue. Let me see one more thing, and after that, we will continue at 4 o'clock, okay? But this limit actually takes time. Usually here, what is the main challenge in this part of this chapter related to limits, okay? I'll see here, most limits, we can just evaluate this directly or just using simple algebraic manipulations, okay? Sometimes actually the main challenge will be, how do we prove that the limit does not exist? Okay, at the time you have to prove this. For example, I know that limit does not exist and I have to prove this. At the time, actually we have to show that since a limit does not exist, if for example we are talking about some kind of point here, that's x sub 0, y sub 0, I had to show that at least two paths, if you just approach this along some kind of path, okay? And I choose another path, maybe something like this, okay? If I can show that when you approach this point along these two different paths, all right, the limiting value of the function, actually it will be different, which means that the limit does not exist. Because by the definition, regardless of your direction, your approaching direction to this point, right? You just approach in this direction or in this direction or in this direction, it doesn't matter. The value of the function must get closer to L. But since if you're going to choose different paths and approaching this point along the first path or another path, if they are producing different values, or in each case, the function is approaching two different values, that means that actually the function does not have limits. Now, actually, this is one example for this, and in our next session, we will practice those things. How do you prove that a function does not have limit at a given point? Okay, boys, let's have some rest. Okay, 30-minute break today, and next time we will say this is the first week, and at 4 o'clock we will continue. We have maybe 30 or 35 minutes, and we will finish limit today. Next time we will talk about partial derivatives. Okay, I will see you at 4 o'clock.